Hello, welcome everyone. I'm your host Clark Dever, and today we'll be covering geothermal energy production. Before we get started though, I just want to mention a few upcoming webinars. On December 4th at 10 a.m., we have a end of year geoscience scavenger hunt and Zoom party, so I hope that some of you will join Nate and myself for that. I'll post the registration links in the chat after I'm done speaking. And then on December 18th at 11 a.m., we have one of our Data Science Challenge launch events. This one is for core values, geological quest, and Jesse Pizzell will be walking you through the challenge, the data set, and the starter notebook in that one. So we hope that if you have an interest in our challenges, you will join us and join the challenge because it's a good way to make a little extra money in the holiday season. So as always, if you're not a member of our community yet, we'd love for you to register at thinkonward.com. That allows you to stay up to date on our future webinars, learn more about ways that you can make money through our contracted projects as a geoscientist, and have the opportunity to solve exciting data science challenges with paid winners in our challenges process. All right, let's get to the reason that you all joined today. Liz Roller holds a master's in geology at the University of Texas at Austin and brings over 20 years experience in geothermal, CCS, and the oil and gas sectors. As a senior geodata scientist at ThinkOnward, she integrates her geological expertise with data science, utilizing AI and machine learning to advance energy exploration and sustainability. Liz's extensive experience includes reservoir management, seismic data interpretation, and basin modeling across global projects, establishing her as a key expert in geothermal technologies and sustainable energy innovation. Liz, take it away.
Hello, everybody. Welcome to our talk on geothermal energy production. Let's have fun. So this talk is going to be about the basics of the subsurface of geothermal. And why do we think that geothermal is so great? There's a lot of different reasons. It's clean, reliable energy that's independent of weather or time of day. So you're not worried about, is it windy out? Is the sun out? Is it nighttime? It's got minimal greenhouse gas emissions once the wells are drilled. So it's a near zero carbon footprint after establishing your power station. Enhanced geothermal systems expand the geographic range to away from volcanic systems. Geothermal can act as underground batteries. It creates jobs, especially in areas that are transitioning away from fossil fuel. Decreasing costs have made it much more competitive in the market. And the potential for up to 60 gigawatts of installed capacity in the US by 2050, which is 8% of the country's electricity. So there's a lot of potential in this sphere. The two graphics I have are just, the first one is temperatures at 10 kilometers in the US. So you can see anywhere that's red or purple is going to be somewhere that, honestly, anywhere that's above yellow is going to be somewhere where would potentially be a good candidate for a certain type of geothermal system. And then this is just the bottom graphic is just in 2021, what was the installed geothermal capacity by region? And I think the red lines are just kind of global hot zones, if you will. So where people would want to target using that kind of energy. So why is ThinkOnward all excited about geothermal? So we just hosted a project, Project Travertine, where we have a geoscientist doing an evaluation of geothermal resources in the Western US. But what we really like about this is using play-based exploration. It's the industry standard for high grading oil and gas prospects for exploration, and applying this technique to geothermal is also rapidly becoming the best practices in that sphere. So we really think this is a good way to very quickly evaluate different prospects to move your project forward as quickly as possible. The resource assessment could contribute to development of more geothermal energy production in the Western US. So what we're going to see today is types of geothermal energy production, types of systems, how production style influences the approach to the energy extraction. What are we as geoscientists concerned about and what sort of data we need to answer these questions, and what sort of models can we make in order to de-risk our prospects. And then we'll look at a few case studies. Oh, and I did not say this before. If anybody has any questions, put them in the chat and Clark will interrupt me to ask them rather than wait till the end so you can get, it's much more like a conversation that way. So there's a lot of different ways to break out geothermal systems. It was actually a hot debate internally between the geoscientists at ThinkOnward how to do it because it's not always cut and dry. So this is the way that we decided to separate them out. There's other ways to do it, but I think this way is one of the better ways. So 3 types of geothermal systems. Volcanic, like the traditional volcanic system, like in Iceland, where you have shallow water being heated by magma, and then production in wells that are generally shallow wells. So that's a pro, shallow wells, less money. There's not really any entropy concerns because the magma keeps heating the groundwater. The con is obviously you need an active volcanic system. The completions are complex, and unless you live in Iceland, they're a little bit difficult to scale. Whereas a hot sedimentary aquifer, which you can find these in sedimentary basins around the world, so it's geographically flexible. It's pretty easy to scale. There's not usually any dissolved minerals other than salt, so you're just dealing with producing brine. So your completions aren't as complicated. The cons are just the wells are deeper because you generally have to get, as you saw in the map, kind of around 10,000, well, around 10,000 feet, basically. Would be that in, I don't know what that is in kilometers, but you know, think a Bakken well. That's about how deep you're going to want to get. And finally, the EGS, which we were talking about earlier, the pros are it is also geographically flexible. So you're just what you're doing. So instead of instead of like the hot sedimentary aquifer where you're producing out of the underground water reservoir, running your power and then re-injecting it, this is the opposite. So you're injecting in a closed system water to heat up and then producing that water to run your turbines. So also geographically flexible. It is scalable, and again, no dissolved minerals. But the cons are even deeper wells than the sedimentary aquifer, and so the completion and the drilling is going to be a pretty high cost. So, as subsurface SMEs, what do we care about? The temperature. It needs to be at least 150 degrees C to work to produce power. There are some systems that use below 150 degrees C. Those get really complicated. I'm not to say that it can't be done. It's just for our intents and purposes, it's much easier and simpler to stay above 150 C. If you want to heat and hot water, below 150 is great. Ideally, we'd want it to be normally pressured, so we care about pressure. It can be high or low pressure, but that just requires a more expensive system. We care about the aquifer, the reservoir quality. If we're working with the second 2 types of geothermal systems, we are either producing out of a reservoir, a sandstone or carbonate reservoir, or we are injecting into fractured granite. So we care about porosity and permeability. We also care about the structural complexity, where are the fractures and faults and how will they affect production. Fractures and faults can either be good or bad. And we care about the depth. Deeper holes cost more money. So what data do we need to determine these properties? What data do you as a geoscientist need to evaluate a basin or area for geothermal production? Same data we always need. We care about well logs. They're going to tell us about the reservoir and depth and fluid content. We care about seismic. Now, working on shore, you're not always going to get seismic. And if you have seismic, it's probably not that good. So it's nice to have. But if you have enough wells, it's not as necessary. And if you're in a basin with only a few wells, it's just like exploring for oil and gas in a new basin. You get like one seismic line and one well, and you just make up a story. We care about temperature logs, and those are even if they come off of a well log header and you have to correct for circulation time, they're still very useful. We care about the geothermal gradient because that's going to affect how deep our wells are. The hotter thing, if things get hot more quickly, that's more ideal because your wells will be shallower. Core data, nice to have. Um, just like the seismic data, it will help constrain our model, but it's not completely necessary, but we have it, it'll give us reservoir quality. And then pressure data. So pressure data will matter for both drilling and completions as well as production. So what models can we build to de-risk our prospects? Um, I'm a basin modeler. I always want to build a basin model. It's generally the easiest one to build, especially in geothermal, because you don't have to turn back time. All we care about is temperature at present day. So with the combination of your wells and your seismic and your temperature logs, you can usually get a good idea for a basin model. We care about the pore pressure prediction. Like I said, you care about mud weight, where you want to set your casing, and how you want to complete your well. And we want to eventually build a reservoir model so we know what are, especially if we're in a sedimentary basin, because the flow coming in and out of, say, like a porous sand reservoir, you want to know what that looks like, and especially after turning on time. So your reservoir model is just going to be a static, what does the reservoir look like right now? And then your reservoir simulation model, you're just going to turn on time. So what are the ultimate deliverables
Hey
that we
Liz,
produce?
we have a couple questions if you want to go back
What's
a
up?
slide.
What's up?
So one, Damien asks, would you be able to advise on reading material about how to estimate reservoir temperature from log header data information?
I it's literally sitting on my shelf, and I get back to you on that because I don't remember
Yeah.
the exact title, but there's any type of intro to petroleum systems text, or online text will help you with that. The correction is called a Horner correction, and it's you just look up Horner correction, and it'll tell you how to do it. It's just a simple spreadsheet.
And then we have a second, it's more of a comment. It says MT and gravity, ambient seismic, much more common than seismic reflection in geothermal. So,
Yeah, because that data is usually much more public than seismic, and depending on what you're trying to do, like if you're trying to go for fractured granite, it's certainly useful, and if you're trying looking at volcanic systems, it's useful. It's less useful for sedimentary basins, but certainly, it's it's in the nice to have category.
awesome. Well, you
Cool.
cleared out the queue. I'll let you get back to it.
Okay, so what are the ultimate deliverables produced? The most important one is going to be play fairway maps, and we will explain in one slide what those are, but they are essentially high grading where all the all the best places that you want to look. It's essentially where is the least risky place to drill. You're going to get your basin temperature model that you've made, and then you'll get your reservoir simulation model, which will tell you about expected production. And with these deliverables, we can develop prospects to hand over to whoever's going to drill it to test and ultimately develop. So play-based exploration. This is the industry best practice to evaluate evaluate prospects to be explored for both oil and gas or geothermal. We're just For geothermal, the risk segments are going to be a little bit different, but it is essentially creating a probability map that goes from 0, so bad, to 1, good, of where you're going to have the best. And I use these 4 here because they're the 4 main ones, but you can, whatever your either like a cost limiting factor or a risk factor, anything like that, you can put it in the map and it'll give you a better idea of where to drill. So the main subsurface ones are reservoir presence, reservoir quality, a temperature window, and a pressure window. But if you're approaching this from more of an economic standpoint, you can certainly put in like distance to grid, or what type of facilities are available, what type of, if you need to pipe it somewhere, what type of pipeline is available. Any type of risk can go into this assessment. Oh, and I just noticed, I should have said before. So we use a lot of images in this presentation. If it has not been referenced in the slide, there's references at the end of the presentation. So if you want to look at this later, the references are in the back if you want to find where the image is. Okay, so let's look at some case studies. The favorite one is always Iceland because they've been doing it for maybe not the longest, but they do it pretty well. And it's a pretty neat system that they have set up. So they've got their wells down to almost 2 kilometers, which are extracting both hot water and steam. You've got you can see the aquifers being heated by the nearby magma chamber. So then you produce the vapor and steam. The vapor is separated into hot water and steam. The steam goes and powers the turbines to make electricity. The hot water gets pumped into heat exchangers to supply heating, which then goes to heat houses. And the wastewater is used to heat roads and sidewalks and infrastructure, so to melt all the snow. And then everything gets re-injected back into the reservoir after use. So it's a pretty neat system that they have. Kind of jealous. And then the second one is the German Molasse Basin. So that is a sedimentary basin. So this is all of Germany. I don't know if you can see my mouse. The Molasse Basin is in the very south of Germany, right up against the Alps. So the basin slowly deepens as you approach the Alpine thrust. And you can see, I'd say half of their geothermal production here, half of it is in the western part of the country. But so in the Molasse, you have water is used for both electricity and heating combined in heating and combined heat and power plants. So you can see the temperature map here. You're getting into the good zone right as you get to south of Munich. As shallower parts, they use it for like thermal baths and heating houses and things like that. And then as you get into the good zone, it will use it for creating electricity. And I thought this was a cool map to see where exactly in Germany what the distribution of the power production is, as opposed to other stuff. And so in the reservoir in the German Molasse Basin that they're producing out of is the Upper Jurassic Malm Formation, which is a karst. And then in the northern part of Germany, I just looked that up today because I was curious. It is also Mesozoic, but I think it's a little bit younger, if I'm not mistaken, what they're producing out of. So what's the future of geothermal? What are people doing right now? In the space, companies like Sage Geosystems are looking at closed loop geothermal solutions and subsurface energy storage. So kind of using the subsurface as a heat battery. Fervo is looking at enhanced geothermal systems in fractured granite that they're using well stimulation, like so they're running frac jobs and and they're more on the data side of trying to use data science to expedite their processes. Geothermal technologies are oil and gas veterans who are working the sedimentary basin side. And I think they have a proof of concept that they set up in the Denver basin. So that should be cool to watch them. And ThinkOnward is partnering with Actual HQ in this space. Actual HQ is a platform that helps organizations plan, collaborate, and implement sustainability initiatives. And so we're partnering with them, taking care of the subsurface side of that. So what can you do to go deeper into geothermal? What pictured here is the effluent ponds in Iceland. So some of the wastewater they kind of put in these ponds, and now they're like a tourist, an everybody attraction. I mean, sounds like a nice hot bath on a cold day. There's a couple different places that the U.S. government has set up with some really nice open source data sets. The geothermal data repository is great. I have been looking through there. There's a couple case studies that are really cool. They have a lot of play-based exploration, play fairway maps for different parts of the country that are really interesting. And they are organized by the National Renewable Energy Laboratory, NREL, and there's some good stuff on NREL as well. Um, as as ThinkOnward, we always encourage you to experiment with what machine learning can bring to the story. It's pretty underrepresented in the space. And as like Clark said, register at thinkonward.com to gain access to future projects and challenges. I think that's it. Any other questions?
So Angie asks, can you speak to the movement to repurpose abandoned oil and gas wells for geothermal energy? What are the opportunities, challenges, etc.?
Um, I think that's certainly a space to look into. I would say that the challenge would be as far as many of those are like plugged and abandoned. So depending on the state requirements, you'd have to, I mean, if you plug it, they're pumping cement down the hole. So it would be, you could twin the well. The upside would be, exactly what you're going to encounter because you have the well log of the well. So like, where everything's going to be. Um, and so I would say twinning the well would probably be the best idea. But certainly that's something I haven't really looked into it. So that was just like off the top of my head, but I thought that would be interesting to look into.
Thank you. And Belkacem asks, we use a seismic network of earthquakes to explore geothermal resources?
No, I'm a geologist, not a geophysicist. So I have an undergrad in physics, but that was a long time ago. Um, I mean, it's acoustic imaging. So, I mean, maybe. Again, not a geophysicist, and I know there's some geophysicists on this call, so I don't want to look like an idiot in front of them by just making
TBD.
something up.
I love it. It was very interesting to me, Liz. The different types of wells were obviously, and this is as a, I'm always the non-technical host of these things, so I learned a lot with every webinar. But that they were so dictated by the basically the substrate, like what was down there determines like your path. Because I was wondering when I first saw the slide, there was three different types of wells, and what was the decision architecture around like what you decide to build. Are there any other considerations besides kind of the composition of the earth that go into determining what approach you might take?
I mean, so like if something's nice and hot and shallow, you can do the most direct approach, which is just to drill a vertical well. Versus if you're trying to exploit something like a sandstone reservoir in a sedimentary basin, you're going to want to drill a horizontal well because that's going to give you the much more capacity than just a vertical well. Given if the reservoir is porous enough, and see, I would always gravitate towards less fracture stimulation than more. It just if you have a nice, 15% porosity sandstone, you can drill a horizontal well and set your packers and you're good. Um, I think that would work. But and then as far as the fractured granite, I haven't really I would do more. I don't know I haven't really looked into what their actual wells that they put in there, but I would imagine depending on the porosity, they probably would also want a horizontal well. Because I think they're also, I was talking yesterday with someone about this. I think they are fracking it because I think if they're just going like to say like a Clarefield situation where the granite's already fractured, I think they don't want that because they want to actually um, use microseismic and frack it so it's like very precise where it goes. And I think that it's whoever's working with Apple is drilling so you essentially drill a center horizontal well to put your frac job in, and then two wells, so one on either side with geophones in there, and so you can very precisely see where the frac went.
Mhm.
So you're targeting like what you want to target and nothing else.
Interesting. That's very interesting insight. Thank you. Uh, Owen, commenting on one of the last questions, says most wells are not high enough temperature to actually produce much power. Also, very different completions. Geothermal wells are larger diameter and rarely plugged or perfed. Um, so that was an input I thought I would share with the group. And then Trevor Johnson asked a question. As a broad observation, it appears that the areas for geothermal power are in remote, low population center areas. Is this observation correct?
That's not necessarily true. Um, if you look at, and in case it isn't obvious, I'm a big proponent of the sedimentary basin one. I think it's the most scalable, but that's absolutely my opinion. And not, I think they're all completely feasible. And I think it's just I'm an oil and gas geologist by background, so I just sort of gravitate to what feels like home. But you've got big sedimentary basins all across the western half of the country, and yeah, the western half of the country is has a lot less people, but there are plenty of places like I'd say the Gulf Coast is one of them. Where is that map? If let me go back to my first slide. So like right here, right where I'd say where the Eagle Ford is produced in Texas and then up into Louisiana, this place, Houston is a huge city. Dallas is a huge city. Austin is becoming a huge city. Something like here is absolutely, I think, a great target to put a proof of concept in and see if you can do it. And it's certainly not, you're not lacking for expertise in how to get down there. I mean, the place you don't even need seismic. You just get all the, especially, it's hard to get well data in Texas, but I bet the government will work with you on this one.
Hmm, interesting. Uh, so Buxom asks, we have old oil wells, dead wells in Algeria. Can we use them for geothermal energy? So how do you approach that question?
And well, and I don't know if they if they didn't plug and abandon them, then that certainly would be a good candidate to re-enter. Geothermal wells, like the person who commented said, are a wider diameter than most um, conventional wells, but I would say in Algeria, that's all going to be vertical wells. So I think it's certainly something to look into, especially if they weren't plugged. If they were plugged, then I would say the same thing I said before. Just I would twin it because you've reduced your subsurface uncertainty um, to knowing what's down there because you have the well log for the well, so you know where you're going to encounter things and what pressure it is and what temperature it is.
So another novice question from the peanut gallery over here. So how long have we been working on these technologies roughly? And then, the other question I have kind of floating around in my head is, just order of magnitude. What's the investment cost to build versus, the estimated payoff? Do you have any knowledge of those type of questions on the more businessy side?
Um,
And feel free to
so
say no. I know
I mean,
unprompted.
look,
I didn't prep you for
I
these
am
questions.
allergic to I'm allergic to business numbers, but that's not true. I worked for oil and gas for a long time. Like it's a business case, right?
Yeah.
So we've been working on geothermal for almost 80 years at this point. Like this isn't a new problem. We just have the technology keeps has finally caught up to where it's becoming much more feasible to do it. Um, since the shale boom, the US is very, very good at drilling wells quickly and a bunch of them at once. We've gotten real good at it. That technology is out there. The knowledge is out there. People know how to do it. Um, and I think so. I'm not going to give a yeah. I'm going to avoid the business question, and I will say it has become cheaper because we're so good at it to drill wells than it used to be. And also the last time I drilled a horizontal well was 2008. So I can give you what it cost in 2008.
No, that's all right. Again, I just was curious as the businessy guy on the call. That's interesting. If we have any more questions from the audience, be sure to get them in. Otherwise, I'm going to ask Liz one more question, and that is, what drew you to this specific area of interest, and what keeps you intrigued?
Out of all the projects that we work on here at ThinkOnward, this one is the most like what I used to do and am good at. So anything that gets me closer to the subsurface makes me happy. So um, yeah,
Awesome.
I like rocks.
I love that about you and our team, the love for rocks and minerals. Well, thank you, Liz. Very insightful content. Deeply appreciate you sharing your experience with us. To the audience, thank you for coming today. Please take a moment and fill out our quick 4 question survey that you'll be redirected to when you close Zoom. It really helps me source speakers that cover topics that you're interested in and provides valuable feedback on how we can improve these webinars. Uh, just thankful again for everyone for your attendance today. You'll receive an email tomorrow with links to the video recording and all of the events and topics that we mentioned during the call. So have a wonderful day.